Hello, and welcome to a voiceover for the first presentation I gave for my physics club. In case you don't know, I run a physics club at Uplands every fortnightly Tuesday after school. In case you couldn't come to those sessions, this YouTube channel is for that. Now, my first presentation was on orbital mechanics and how we exploit it. Now, without further ado, let's get on. What is in this session? Well, I split it down into 3 sections in the conclusion. My first section is on general orbital mechanics. Now this is all about how physics works in space and terms we use. Section 2 is on the usage of orbital mechanics. So this is taking our knowledge from section 1 and applying it to spacecraft. And section 3 is the exploitation of orbital mechanics. That's taking our knowledge from the last 2 sections and applying it for a space mission. And then finally, we have a wrap-up on what we discussed and a puzzle. So section 1, general orbital mechanics. How do we get to orbit? What terms do we use? And what rules we apply in space? This will be covered in this section. So, what is orbital mechanics? The application of ballistics and how gravity affects this on space objects. That is what orbital mechanics is. Now, to break this definition down further, ballistics is the field of mechanics that is concerned about trajectories. And a trajectory can be thought as the path a projectile takes under motion. So what are in trajectories? Well, let's say we have a stick figure throwing a ball. What path would the ball take? Well, ballistics predicts that it will go in an arc. And animating this, you can see it sort of follows that curve. Now, I want you to try figure out a point in this trajectory that we might be interested in. If you rewind time a little bit, maybe this point would be interesting for us. Why is that so? Well, look at the height between the ball and the ground. What can you say about this? It's at its maximum height, and we can give this point a label. This is called an apoapsis. It's the highest point during the trajectory. Now, is there anything else we can pick from this? Not necessarily a point, but what happens to the ball? Well, if we rewind time a little bit more, what can we say about the ball when it is thrown? Well, you can say that it had no velocity, but it was given a change in velocity in order to have a trajectory. Well, we can write this as delta v, the little triangle meaning change. Moving on, what is a suborbital trajectory? Well, the trajectory must collide with a body which gravity influences it, like Earth. But me jumping up and down, I don't think I would call that a suborbital trajectory. So what else can we add? Well, we can say it must have been in space. So therefore, its apparatus has to be in space. So for Earth, space starts 100 kilometers above the surface, and this is known as the Kármán line. So what's an example of a suborbital trajectory? Well, Jeff Bezos' New Shepard reached an apparatus of 107 kilometers, and by our definition, that made him complete a suborbital flight. But a fun fact is that Richard Branson only reached 90 kilometers, so he did not complete a suborbital suborbital trajectory. Now, how much delta V, change in velocity, would a rocket need to have a suborbital trajectory, in case you grow up to be a billionaire or something? Well, our objective here is to reach 100 kilometers going directly up. Now, since this is physics, we can make some assumptions to make the calculation easier. We can say we apply this change in velocity instantaneously to have the most efficiency. So if you were driving a car, the most efficient usage of your fuel is to accelerate once. And we can also remove atmospheric drag to prevent energy loss to the atmosphere. Got this? Now I can calculate it. The conservation of energy states that energy is transferred, not created or destroyed. So in this scenario, energy is transferred from kinetic energy into gravitational potential energy. So we can say that Ke equals GPE. And if you substitute our formulas for both of those equations, we get half mv squared equals mgh. Now we can simplify by cancelling the terms to get a half v squared equals gh. Now we want to find what velocity is, so we need to rearrange that. So we move a half over to get v squared equals 2gh, and then we square root it. Now we can finally calculate the delta v a spacecraft would need to reach a suborbital trajectory. So if we substitute unknown values, which is g and h, we get v equals the square root of 2 times 9.81 meters per second squared times 100,000 meters. And the numbers say that our velocity required is around 1,400 meters per second. So we calculated that we need 1.4 kilometers per second to reach space. And this is sort of accurate, as it's the same amount of delta V Spaceship One, which is Richard Branson's first space plane, had. Of course, in real life, it would be more because we omitted any losses. Now, moving on to an orbital trajectory. What is the definition here? Well, the trajectory must not collide with the orbiting body, like a planet. Otherwise, it would be suborbital. So therefore, its lowest point must be in space, and we can call this point its periapsis. Now, in order to have it orbit, its apoapsis must be within the sphere of influence of the orbiting body. The sphere of influence is just the range of where the planet's gravitational field is most dominant. Now, it takes 9.3 kilometers per second of delta V to reach low Earth orbit, which is 6.6 times higher than having a suborbital trajectory. So what's the difference between a suborbital rocket and an orbital rocket? Well, luckily, we have a great example of this. Let's go and compare two different launch vehicles designed for a suborbital task and an orbital task. I've chosen the Mercury Redstone and the Mercury Atlas because it carried the same payload, which is the Mercury capsule. For a brief history lesson, the Mercury Redstone delivered NASA's first astronauts into space, while the Mercury Atlas delivered NASA's first astronauts into orbit. So for the Mercury Redstone, it had a mass of 30,000 kilograms. It had a height of 25.41 meters. It had a diameter of 1.78 meters, and its propellant was ethanol, which is what early rockets used. Now, this overall made the Mercury Redstone have 2.33 kilometers per second of delta V, so enough to get into a suborbital trajectory, but not enough to reach that 9.3 we need to have for an orbital trajectory. Now, the Mercury Atlas differs. Its mass is 4 times greater at 120,000 kilograms. Its height, a bit bigger, at 28.7 meters. Now its diameter is around 3 meters, but this is not including the bottom bit where the engines are, which is a bit bigger. And its propellant was RP-1, which is rocket-grade kerosene, and this is what later spacecraft use for their launch vehicles. Now this overall made the Mercury Atlas to have a total delta V of 9.4 kilometers per second, so just barely enough to get into orbit and back. Now, once you're in space, you have some rules to follow. But don't worry, we can simulate these rules using a program called Kerbal Space Program. Now, if you're interested in rocket science or anything like this topic, I encourage you to check it out. But moving on now. One of the rules we have to follow is this. If a force is applied at apoapsis to the highest point, or periapsis lowest point in an orbit, it will do one of the following effects on the opposite point. If thrust is applied in the direction of motion, it will raise the opposite point. Now, if thrust is applied against the direction of motion, it will lower the opposite points. Now we can watch this in Kerbal Space Program. So here we are in orbit, and we're going to apply thrust in the direction of motion. And now we can see that our apoapsis is increasing. If you think back to the first rule I just covered, it follows what it says. Now we're going to switch directions and burn against the direction of motion, and we'll see what happens. Now our apoapsis is decreasing in height, and that also follows the first rule. Now something strange is going to happen right here. Since the apoapsis has to always be bigger than the periapsis, if it goes below the certain height, the nodes swap direction. And now the periapsis is decreasing in height. Now the second rule. If an object is closer to the orbiting body, it will move faster relative to the surface of that orbiting body. Now we can watch this in Kerbal Space Program again. So we have two spacecraft here, one in a lower orbit and one in a higher orbit. And we can see that the one in the lowest orbit is moving faster relative to the surface of the planet than one in the highest orbit. See, the one in the lower orbit has completed one orbit already, while the other one has only completed half an orbit. Now, Rule 3 is a continuation of Rule 2. The orbital period, which is the time it takes to complete one orbit, squared, is proportional to the cube of the average distance from the center, not the surface, the center of the orbiting body. Now, you might come across this as Kepler's third law. Now, these three rules will explain what spacecraft plan around, but also what we exploit to create missions. Gemini 4 had a series of tasks, and one of them was to try and rendezvous with the spent Titan II booster it flew up on. So the commander, James McDivitt, attempted this. Now, it seems a simple task, right? If you just burn your engines towards the target, it's that easy. However, that's what James McDivitt thought when he orientated his capsule around and used his engines. What he actually found is that the Gemini capsule was beginning to move downwards and then also started to move backwards. But that makes no sense without understanding the rules we've covered. Let's try and apply the rules we know. You burnt against the direction of motion, where the Titan II booster was, in a circular orbit. Now, in a circular orbit, all the points are the same height. So we can say that all points are at an apoapsis or periapsis. Now, what rule concerns apoapsis and periapsis? The first rule. So we can apply this here. He burnt against the direction of motion, so he lowered his periapsis. Now, as he seemingly drifted towards the Titan II booster, we can explain his downward motion as his periapsis was lower, so therefore he was starting to move lower and closer to the Earth. But then there's also another rule we can apply here. He was moving faster relative to the surface as he got closer to the planet from rule 2. So he started to move faster than the Titan II booster, which was behind him, which explains him moving away. Now we can act this out in Kerbal Space Program. We have a target we want to reach. So if we open the map, we have a target behind us. So we're going to do what James McDivitt did and burn towards the target. Now, we can confirm here that our periapsis is lowering from the first rule. Let's burn a bit, and then let's speed up time and see what happens. Keep an eye on both objects. So we're getting a bit closer, but now we're starting to move downwards. Now we moved really downwards, so that shows us our downwards motion. But now the second rule begins to act, and we start to move further away. You can see halfway through the orbit, we have downwards motion and backwards motion. At least that shows what James McDivitt observed. And as we complete one orbit, we can see that instead of getting closer, we've only separated. So that was the first section. Now moving on to section 2, the usage of orbital mechanics. How can we use orbital mechanics to aid us? And more specifically, how does this help with travel? There's a problem every spacecraft faces. Each rocket must have a set amount of propellant that we can bring along with the mission. Now, we use this propellant to move and orientate in space, draining it. So here lies the problem. Running out of fuel. Now, let's try and fix this. So we have a satellite here that doesn't have enough delta V to complete its mission. We can suggest one of the most obvious ways in solving this task. Just add more fuel. So we add some propellant tanks, and that means that the spacecraft now weighs more. But this means that our launch vehicle doesn't have enough delta V to get us in space. So we increase its fuel, but now it weighs too much to lift off. So we add boosters, and while this completes our task now, it's too expensive to build. But there's more, and this relies on rocket equation, which is this. Now let's try and unpick what this means. We've seen delta V before, that is just a total change in velocity. Now we have VE. What does this mean? It's something to do with velocity, but what exactly? Well, it's the velocity of the ejected material. Rockets produce its thrust by throwing out material from its rocket engine at high speed, and that speed is v. Now we have ln, which is the natural logarithm. Finally, we have m0, which is the launch mass. So this is the mass of the rocket with fuel, and we have mf, which is the mass of the rocket without fuel. m0 divided by mf is known as the mass ratio. Now, where does the problem of adding more fuel lie in? It lies in the natural logarithm. Simply have to find the natural logarithm of the mass ratio. Now I can say that the total delta V is proportional to the natural logarithm of the mass ratio from the rocket equation. So let's plot a graph and see what happens. We can put mass ratio on the y-axis and the total delta V on the x-axis. Now here's a demonstration of the problem. Say we had a mass ratio of 10. We have a total delta V of 2.3 something. Now if we have a mass ratio of 20, that goes up to 3. So that's pretty good. But if we go from 20 to 30, we get less out. If we add more fuel, the mass ratio will increase, as the launch mass of the rocket will increase more so than the dry mass. So if each unit of propellant we add will provide less delta V than the last unit. So therefore the solution is not sustainable. So we have to come up with a different way. If you can't bring more fuel, how about we use less fuel? But is there anything that allows this? Well, we can introduce the Oberth effect. The Oberth effect is this. The use of a rocket engine at higher speeds generates a greater change in mechanical energy than the use of it at lower speeds. And mechanical energy is kinetic energy, which is related to velocity, which is what we want. Now, if we have an orbit, where would the Oberth effect apply? Think back to rule 2. It would be here, right here, at periapsis. But why is that? Well, we need to take a quick detour onto how a rocket engine works. And why is this important? A rocket engine accelerates mass in the form of hot gases to a specific velocity, and this gives the mass momentum. Momentum equals mass times velocity, so therefore we give hot gases momentum. Now, the conservation of momentum means that a rocket also gains the same amount of momentum in the opposite direction. Now, force equals a change of momentum over the change of time. So a force is applied to a rocket. No, momentum is proportional to velocity at any point in the orbit. So therefore, an engine transfers the same amount of momentum per unit of propellant anywhere in space. However, this is not true for energy. So why does the Oberth effect exist? Let's say we have a scenario here. We have a rocket that weighs 2 kilograms. Now, it provides 1 meters per second of thrust anywhere it is. From the last slide, we can prove that is true. Now, from the second rule, its velocity will be higher the closer it is to the planet. So what links velocity to energy? Kinetic energy, E equals half mv squared. So let's work out the change of energy at 2 points. The point 1 at apoapsis. Let's say that the rocket is moving at 1 meters per second before ignition. Now it burns in the direction of motion and provides a change of velocity 1 meters per second prograde. Now it is moving at 2 meters per second after ignition. Let's calculate the change of energy. We work out the energy beforehand, which is 1 joule, and we work out the energy after, which is 4 joules. 4 joules minus 1 joule equals 3 joules. Now, let's have a second point at periapses. From the second rule, we say this is moving faster. So we can say it's moving at 10 meters per second before ignition. It still provides a change of velocity of 1 meters per second, so now it's moving at 11. Like before, we work out the energy before and the energy after. Now, calculating the change of energy here, we have 21 joules, and this is an 18 joule difference from apoapsis and periapsis. So we gain 18 joules from the O-width effect. So let's try and expand this. We found a way to minimize our fuel usage at one point. Let's try this approach to a whole mission. A more general way to maximize efficiency is to use a rocket engine as little as possible. So if you want to go from one orbit to another, we can say that we have one burn to just one axis, so that's apo or periapsis, and the other burn to just the other. And this is called a Hohmann transfer. It starts out with an initial orbit, then a transfer orbit, and finally our target orbit. A Hohmann transfer is generally the most efficient way to go from one orbit to another orbit. However, there are scenarios where there are other transfers that are more efficient than this. So putting this section together, using orbital mechanics, we successfully found an efficient way in conserving propellant, and also this way can be universally applied to any space mission. But the question now is, can we design an entire mission around the exploitation of this? That moves on to the last section. Section 3, the exploitation of orbital mechanics. How do we use orbital mechanics to fulfill the requirements of the mission? How do we plan using this? So you are the CEO of a new space company, SpaceY. Someone wants you to launch 3 satellites. However, they need it to function in a specific way. The contract is laid out at you, and these are the terms they want you to do. These 3 satellites must be in constant communication with each other. At no point should they lose communication. However, each satellite must also be in constant communication with a respective ground station back on Earth. And you have to do this as cheaply as possible. So let's try to visualize a solution here. We have the Earth with 3 ground stations. And the contract asks you to do this as cheaply as possible. So let's place the satellites in the cheapest orbit, which is as close to the Earth as possible. However, they cannot communicate with each other. The Earth is blocking that. That's no problem. We can raise our satellite's orbit to a higher orbit, and we can see that they are in communication with each other. Now, what about the second part of the contract, where it must be in communication with the ground station? Let's just focus on one satellite for the moment. See, the satellite will orbit, but also there are spins. So if we simulate this, we can see that the satellite is moving faster than the Earth, spinning, and it loses contact with the ground station. The satellites orbit too fast. That is our problem. However, is there a rule that we can use to try to solve this? Kepler's third law comes to mind. The time taken for one orbit squared is proportional to the height of the satellite cubed. So what if we make the time taken to complete an orbit 24 hours? Let's go with Kepler's third law. We know that the time taken for one orbit squared is proportional to the height of the satellite cubed. We can write this as t squared is proportional to r cubed. But we need a constant to make them equal each other so we can actually calculate this. And Kepler came up with this. Now t squared is the orbital period and r cubed is the radius of the orbit from the centre of the body. Now the constant here is the middle part. We have pi, but we also have g and m. Now m is the mass of the thing you want to orbit, so in this case Earth. Now we have g, which is the gravitational constant. So let's try to calculate the height of a geostationary orbit. Rearranging for r cubed, we get that r cubed equals t squared times by gm over 4 pi squared. Now plugging in our values, we get that the radius cubed must be 7.53 times 10 to the 22 meters. So if we square root this, our radius is around 42 million meters. However, this is calculating from the center of the Earth. We need to correct for this. So 42,000 kilometers minus 6,000 kilometers, we get a radius of our orbit of around 36,000 kilometers. And this is close to the actual height, which is only 300 kilometers below our calculated value. So now, having our orbit established, how are we getting there? Well, let's say we have the Earth and our intended orbit. One way is just to launch each satellite on its own rocket. So up goes the first satellite into position. Up goes the second satellite into position. And up goes the third satellite into position. But rockets can explode. So not only this was really expensive, you've destroyed one of their satellites, and they're not going to be very happy about that. So let's try a different approach. Let's say we launch all 3 satellites in one rocket. Now this is good for them getting into orbit, but they're not in their intended positions. How can we get them into their intended positions to fulfill the contract? Well, if you think back to Gemini 4, what did James McDifford do? He burnt May's periapsis lower, and that ended up him separating from the Titan II booster. So let's try to apply this here. Let's have one of the satellites go into a higher orbit, represented by the golden orbit, and one of the satellites go into a lower orbit, represented by the blue orbit. Now if we animate this, we can see that the satellites will go on their respective orbits. Now the lower satellite, since it's going closer to the Earth, it will speed up and complete its orbit first. Now all the satellite can do is correct back into geostationary orbit and just let time play again. Now our second satellite has completed one orbit, and since it's already in geostationary orbit, it is fine. So we just wait a bit more. And now our third satellite is in position. So we correct its orbit, and we have our satellites into their correct positions. So we have a successful mission here. We designed a unique mission to fulfill specific requirements using the knowledge we know about orbital mechanics to our advantage. Wrapping everything up, we learnt what orbital mechanics is, along with some simple rules behind orbits and how unexpected results can be broken down into our understanding. Then, we've taken that knowledge and applied it to a universal problem that every spacecraft faces, and we've provided a solution without expense. Finally, we use these rules to design an entire space mission around the strict. Finally, we use these rules to design an entire space mission with strict parameters around with. But before we finish, there's a puzzle we can do. This is the Monty Hill paradox, and it works like this. You're on a game show where there's 3 doors. Behind one of the doors is a prize. However, behind the others are goats. Now, the game show host asks you to pick one of these doors. So let's say you pick this door. Now, before opening that door, he goes around and opens another door, which he knows that there will be a goat behind. Now, he offers you this choice. Do you want to switch your choice, or do you want to stay? What would you do? And now this ends the session. I hope you enjoyed it.